Okay, so we are going to look at ionic addition, the mechanism. You've had the opportunity now to see it done on the board. We have said that if it comes from a reaction scheme, it might look something like C2H4 becomes C2H4Br. My suggestion has been draw out your structures because that's going to help you to see what is going on. So the fact that there is the double bond here must mean that it is going to be an addition. We have said with any addition we're going to make it on to the opposite sides, and the reason for that is because each of these bromines has 4 electron shells by old school Bohr, similarly over here, and because they're so large they'll try to get as far apart from each other as they possibly can. So what do we have as we go left to right? Well, we have added on these bromines, so it must be an addition, and our reagent in this instance is Br2, no catalyst. So I have said that when I'm doing this, I draw my formula here on the left and I draw my formula here on the right, and I start my ionic addition in that way. Okay, and you know I'm going to work down the page for a point and then work up the other side. So here on the left hand side I have ethene. Bromine is the molecule of interest, and bromine will always approach it perpendicularly to the double bond, so that's really important that you keep that perpendicular shape. We have said because the double bond here has a sigma bond between the carbon atoms and a pi bond above them, so the electron pair in the shared pairs are rotating in 3-dimensional space around the sigma bond, and this makes them very reactive. They want to react, so for that reason when they do this they polarize the bromine underneath them, and what that means is that the electrons in the shared pair here will go toward the bottom bromine, and the top bromine is more positively charged, and these negative electrons are looking for them. So I'm just going to erase here and erase here. So because those pi bonds have polarized the electrons in the double bond, one pair of them are going for this bromine, and the electrons that are shared between the bromines are going to go on to the delta negative bromine. So we have 3 things that we always have to put in. We have to put in our perpendicular bromine to the ethene double bond, we have to put in the delta plus and the delta minus, and we have to use these curly arrows. So those 3 things are really important for the first diagram. Now there are 2 pieces of blurb that you can write for the first diagram. The first one is we show it in the diagram, so it's not hugely necessary, but what we say is that we get polarization of bromine by the double bond in ethene. So originally the Br2 is going to a Br with a delta positive and a Br with a delta negative. So we show that in our diagram here. So that's already shown. So that's not the end of the world if you don't write that down, because you've shown it in your diagrams. So that is the first sentence. It's this second sentence is what we don't see when we go from diagram 1 to diagram 2. And once the electrons in the shared pair up here have gone for the double bond, or the electrons in the double bond have gone for this top bromine, what we have happen is heterolytic fission of bromine. So what does that mean? So heterosexual, it is the opposite, and lytic, it comes from lysis, meaning to split. So if this is my bromine with my electrons equally shared, because bromine is a non-polar molecule, what happens in this split, is one bromine gets no electrons and the second bromine gets both. So that looks like then in a formula when you draw it is the fact that we now have a bromine that's positively charged, which is this one, and we have a bromine which is negatively charged, which is this one, because it's ending up getting both electrons. So if you were to write a sentence, we say heterolytic of fission of bromine. I'm just going to remove this. So we have heterolytic fission of bromine to form Br plus and Br minus. So this would be the little equation that would explain that. So that's our first step covered. In the second step now, we're showing the product that results after the electrons in the double bond are going for the delta positive bromine. So we have broken our double bond. We have said we're putting any addition of bromine out to the side, and we are now left, because the electrons in the original shared pair are up here now, we are left with this molecule. This is called, in terms of a general structure, it's called a carbocation, and I would like you to write this down next to it every time you draw it. Because the addition that we've made is this bromine here, we can also call it a bromonium ion. So you can label both of these things if you so wish, but definitely this one. And you may see this one in a question and it will help you to understand it. Now this intermediate is really, really important, because this is the reason why it's ionic addition. This will not form by any other mechanism. So when we talk about evidence later on, the evidence will be on the basis of what negative ion can attach to this carbocation. Okay, so we have this positively charged moiety sitting in our solution now, and again that's going to be really reactive. So we have the carbocation, and we also we have a bromide ion left now. It's going to keep getting rid of things, so we just ignore it and drive on. So the second thing that we have left down here is a bromide ion. So this got both of the electron pairs, and opposites attract. So in diagram 1 we drew our arrows down. Here we are drawing our arrow, and it's going to go for this. And the final diagram that we draw is the diagram that is up here. And the last thing we do is we name. So this is carbon 1, this is carbon 2, or you can reverse it, doesn't matter. So I have bromines at positions 1 and 2. I have to tell them that what is attached. There's 2 bromos, and it is an ethane now, because it's saturated. So they are your steps in ionic addition of bromine and ethene. In terms of now the pieces of evidence that we look for, there are 3 pieces of evidence. I'm going to actually go back here. So what we haven't said, and I apologize for that, is what are the blurb that you could write for step 2. So in step 2 we can say that addition of bromine to the double bond forms an intermediate carbocation, or in this case only the bromonium ion. So all of the intermediates we're going to draw will be carbocations, but this is the only one that is a bromonium ion thus far because of this bromine over here on the left or on the right. Okay, so that's step 2. So it's telling us about the carbocation, and the final step is describing this second picture. And the second picture is telling us that we now have addition of bromide to our carbocation, forming one, oh, I always do that wrong, apologies, 1,2 dibromoethane. So there are 3 steps. As you said, it's the only one that isn't explicitly shown in the diagram is the heterolytic fission of bromine. So if you wanted to write that after your diagram 1, you absolutely can. You should hit everything with your diagram marks, but just in case, make sure that you put that in. So we're going to talk a little bit about evidence, and before I do that, all I will say is, so I do my diagrams 1, 2, and 3, and the reason I do that is because in diagram 1, my arrows go down, my arrows go down. In my diagram 2, as soon as I drew my cation, my arrows go up, and then my last thing going here. So I use the down to tell me where my down arrows are going, and I use the up to tell me which arrows go up. You can absolutely draw this as 1, 2, 3. You can put your pieces of blurb in between it as you go. The choice is yours. So we have to figure out the evidence for this, and they will either ask it as a general question, which will say, give a piece of evidence to prove ionic addition. So that's a real general statement, so you have some choices, or they will be very specific, and they will say something like bromine water containing sodium chloride. So we have said, or I have said, that the key piece of information in the last one that we did is the formation of the carbocation. Because of this, any negatively charged ion in your solution is going to attach to it. So we know from going through our mechanism that we will absolutely have Br minus is going to be in there because of what happens to the bromine. So when this joins to this, it makes our expected product. So the expected product is going to be the 1,2-dibromoethane. That is expected. So if you were showing your piece of evidence for this scenario up here, then you could draw your bromide ion attaching to this, and then you draw your end product that goes with it. Okay, I'm not going to fill in the H's here, I'm going to be lazy. So that is an expected product. With this statement up here, they want you to recognize what are the negative ions in these things. So we will look at sodium chloride first. So when we put sodium chloride into water, NaCl, it dissociates. And it dissociates into Na plus Cl minus. So now in my solution I have some Cl minus ions floating around. So what's that going to mean for us? So what that is going to mean is that now this Cl minus can now be attracted to the carbocation. So if that is the case, then we now make something that looks like this as our product. Okay, so that is unexpected. So how do we name it? Again, the rule is when you put on side groups, you name them alphabetically. So for that reason, I'm going to make this carbon 1 and this carbon 2. So my expected or my unexpected product here is going to be 1 1,2-bromochloroethane. So this unexpected. So we've dealt with our expected down here. We now have something that is unexpected. So this is one unexpected product, and we get this product if there is sodium chloride in our water. So 1,2-bromochloroethane unexpected, and it came because we had sodium chloride in our water. So then the last one that we're going to look at is going to be the water itself, because water will dissociate and form ions in solution. Okay, so this goes back to when we were looking at ionic bonding and how do things solubilize. So if you put salt into water and it's going to dissolve, the reason it dissolves is because water itself has dissociated into, okay, I'm not going to go there now. For now, I'm just going to start with this. So water dissociates. I now have this anion in my solution, and as before, because of having a positive carbocation intermediate, the OH minus will be attracted to my carbocation, and we will make the following molecule. So we get CCBr OH H H H. So what have we made now? So again, our second unexpected, this group here, when it is attached, is an alcohol group. We always do our naming from the lowest carbon, so this is going to be carbon 1. So in this case, I have made 1-bromoethanol. And the reason now it's ethanol is because this is 2 carbons. So eth, and it's an alcohol functional group. So I make 1-bromoethanol if there is water present, and I make 1,2-bromochloroethane if there is sodium chloride present in my water. So we have 2 unexpected products that we only get because of ionic addition. So here ends the first video.